This Explain Everything video is intended as an instructional resource to help teachers better understand the article as described in the teacher notes. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. We chemistry teachers all teach our students how to draw Lewis structures, but unfortunately our students don't really understand how these can be used to explain and predict the properties of substances. Furthermore, Cooper and Klymkowsky state that beginning students need non-trivial knowledge that they don't possess in order to be successful drawing anything but the simplest structures. On page 869 of the article, the authors advocate a constructivist approach that is quite consistent with modeling instruction. The authors state that unless the instructor adopts a Socratic role and guides students to build on their previous knowledge and resolve difficulties, students may feel that rote learning is either necessary or sufficient. That is, the new knowledge need not be connected to or reconciled with their pre-existing cognitive structure. It is memorized but not understood, and more likely than not, quickly forgotten. For example, take the molecule C2H6O. Students might have difficulty figuring out which atoms are connected to which. Here's one structure that students might come up with, but it's just as likely that students could connect the atoms this way. One would hope the students would remember these two examples from the previous worksheet, but if the students view drawing Lewis structures as some set of rules, they may not make the connection to their previous understanding of valence electrons. The authors point out that the problem gets even worse as the molecules become more complex. Here is the example the author's cite is drawn by an organic chemistry student. But a search on Wikipedia shows many other possible structures. Propanamide, acetone oxime, 1-amino-2-propanone, and dimethylformamide are just 4 of the common isomers of this molecule. Interestingly enough, the structure that the organic chemistry student drew is not one of the common isomers. Even for simple molecules, structural cues can really help. For example, given the formula CH4O, the authors found that about 60% of the students got the structure correct. But if the structure were written as CH3OH, then over 90% of the students got the structure right. So it would be worthwhile to have a discussion after you do the last problem on worksheet 5 to see how students may have struggled trying to figure out which atoms were connected to which when the formula was written as CH2O2 rather than HCOOH. Just as we do in our approach, the authors suggest the difficulties associated with students relying on anthropomorphic explanations when they're trying to construct their Lewis structures. For example, when they say that elements want or need a certain number of electrons to make them happy or stable. So in this case, with NH2, a student put 8 electrons around nitrogen to complete its octet, despite the fact that the molecule only has 7 valence electrons. When it comes to molecules that have an odd number of valence electrons, students have difficulty deciding where to put the lone electron. Sometimes they end up even putting expanded octets on second period elements, as in these representations of nitric oxide. So we shouldn't make drawing the structure the goal of this exercise. Instead, Lewis structures are a tool to help students make sense of the chemistry they are learning.